Hey, how's it going? Before we jump into the content, I just want to take a minute to thank you for stopping by the channel and checking out the content. If you like this content and you want to support more content like it, then make sure to subscribe to the channel and like this video. You can also check out the YouTube membership program and cybertrainingpro.com, where I put practice exams and other things that I couldn't put on YouTube. Again, regardless of how you support the channel and my content, I couldn't be more appreciative. Thank you so much, and let's get into the content. When it comes to switches, there's basically two major categories that you need to know about. We have unmanaged switches that provide almost no configuration capabilities. Basically, you just plug devices into these switches and they work by transferring data across the data plane or the forwarding plane. Typically, you're going to find these switches in home offices, small businesses, or other environments where you don't want additional features or you don't have the manpower to actually manage them. And then we have managed switches that run separate from the data plane, and they have specialized operating systems. With these switches, you can add additional features that operate on what's called the control plane. These kind of switches are very common in medium-sized businesses and larger. With managed switches, you can connect to them using a serial interface, a serial to USB converter through SSH, or through a built-in web interface. Managed switches typically have a port called a console port that you plug a cable into, and using a terminal program like PuTTY, you can access the command line of the switch. On Cisco managed switches, you'll see the console port usually on the back of the device. These switches get their initial configuration through that console port. Basic configurations are like any device, and they include an IP address, a default gateway, a DNS server, and you might also have to update the firmware. Access management on managed devices is extremely important. This means that you should configure a username and password for authentication and decide if you're going to allow remote access, which is called in-band management, or if you want to configure a management port, which is going to require a direct connection or a connection from a more secure network to perform out-of-band management. If you're going to use the web interface console, you need to make sure that HTTPS is enforced. Port configuration is also important because there's usually speed, duplex, flow controls, jumbo frames, and more settings that you can configure. The actual syntax is going to vary by the switch manufacturer. However, common commands include show config, show interface, show route. Especially on Cisco specific devices, those are very useful commands. The cool thing with port security is that if it detects a different MAC address, the switch can immediately shut down that port. Port security can also limit how many devices are connected into that port and shut down the port if too many devices are connected. That way somebody can't just bring in their own switch or their own wireless router and expand the network, because it will detect all those extra devices. Port security is a feature that locks a port down to specific MAC addresses. Cisco switches in particular have a feature called Sticky that will dynamically grab the MAC addresses that are plugged into that port, but you can also manually configure these. One problem that comes up with switches is that if you plug lots of devices into a single switch, they all become part of the same broadcast domain. If you have enough devices plugged in, this can lead to a large amount of broadcast traffic and other potential issues. VLANs, or virtual local area networks, allow you to logically segment a switch into separate networks without needing additional hardware. This also makes each one of these new networks a separate broadcast domain. When you first start a switch, every port starts in a default VLAN, which is usually VLAN 1, but you can select the specific ports or a port range to belong in a specific VLAN like VLAN 1 or VLAN 20. You get the idea. It's a good security practice to change that default VLAN to something other than VLAN 1 to harden your network more than when you use the default settings. So let's say that you have two switches, each with VLAN 10 and VLAN 20, and their systems connected to each VLAN on each switch. If you want these devices in each VLAN to communicate with the devices on the other switch, you're going to have to connect the switches together using something called trunking. Now, trunking allows VLAN traffic to travel between the two switches as if it were one big switch. In order for this to work, you need to configure a trunk port using the IEEE 802.1q standard, which is going to be the port with a cable connecting the two switches. The nice thing with managed switches is that there's no specific trunk port, so you get to decide which one you're going to use. The 802.1q standard does something called port tagging, which means that it assigns traffic a tag and a field assigned to a frame's Ethernet header so that it can be assigned to the correct VLAN. These tags only exist if the traffic is traveling across that trunk. The ports where the systems are directly connected to are called access ports or untagged ports, and they help assigning traffic to the correct VLAN. A key point is that all switches have something called a native VLAN, and any untagged traffic gets associated to this VLAN. That means that if traffic is destined for the native VLAN, even if it's sent onto the trunk, it's not going to receive a tag. Native VLANs are vulnerable to something called a double tagging attack, and this forces modern networks to not use the native VLAN, and trunk ports are actually configured to tag native VLAN traffic. Alright, so we know that we can configure ports and VLANs on different switches, but is that something that we want to manually do? Of course not. Luckily, Cisco has a proprietary protocol called VLAN Trunking Protocol, or VTP, that can actually automate the process of updating VLAN switches. VTP has 3 states that you need to know about and that can be set: server, client, and transparent. The big idea is that if you want to make a change on a VTP server switch, then all the connected VTP clients get updated automatically. Transparent mode tells a switch to keep its manual settings and not update, but if changes happen on that switch, then they'll be sent out to the other switches in the VTP domain. What happens if you want to send data between VLANs? Well, by design, this process, which is called inter-VLAN routing, is not possible without a router or a multi-layer switch. One way to actually accomplish inter-VLAN routing is if you have a router with multiple ports, you can connect switch ports assigned to each VLAN into separate ports on that router. Another way is router on a stick, or ROAS, which is a more popular option that only uses a single port on the router. The configuration of that router interface is broken into sub-interfaces that handle each VLAN. Introducing a router to perform this function isn't always the best option, so there are multi-layer switches or layer 3 switches that can perform all the normal switching functions, but they can also perform routing, and they can also handle inter-VLAN routing. One downfall with DHCP is that DHCP requests are sent as broadcast messages and they can't pass through a router. Fortunately, relay agents, or DHCP relay, is a feature that can be enabled on a router so that DHCP messages can be passed on to other networks. If you're on Cisco gear, the IP helper command is what you need to enable DHCP relay support on port 67, and it also enables relaying for TFTP, NTP, TACAX+, DNS, NetBIOS, and NetBIOS datagram. It's not uncommon to have separate voice VLANs specifically for voice traffic. Usually you'll have quality of service for this type of traffic, which means that that voice traffic gets prioritized over other data traffic. Think about it. If voice traffic is choppy because it's second priority to data, it's not very useful. Private VLANs are useful if you want to separate traffic from systems or locations. They only allow traffic from private ports that are assigned to the private VLAN to be switched to the uplink trunk port. Basically, these ports are isolated, so they can't see anything else going on in the switch. Troubleshooting VLANs really comes down to VLAN assignment. If a system can't reach resources, its port might not be assigned to the right VLAN, and you'll have to see the switch's configuration to actually verify that VLAN assignment. Based on our discussion regarding switches, we know that switches are a layer 2 device of the OSI model, and they forward traffic based on MAC addresses. Multi-layer switches, or layer 3 capable switches, forward traffic based on IP addresses and basically can do the same job of a router. They also do all the normal switching functions that happen at layer 2. If we look at Cisco layer 3 switches, you'll have both a switch port and a router port option to distinguish which type of port something is. The big reason for this is because routers and layer 3 devices transport data using IP addresses, so each routing port needs an IP address. On the other hand, layer 2 devices work based on MAC addresses, so an IP address isn't required. Let's talk about some of the common functions where we can use a multi-layer switch. Something I want you to keep in mind is that if a device works at multiple layers of the OSI model and performs more than a single service, it's considered a multifunction network device. You may not realize it, but there are some devices and organizations that handle millions, billions, or trillions of connections per year. For example, a website like Google does not have a single web server because it would crash almost instantly. Load balancing is the ability to make multiple servers look like a single server and they form a server cluster. The idea is that you make a request to what seems like a single server, and on the back end, traffic is distributed to servers to ultimately give the best performance. DNS load balancing is fairly common and is where all of your servers, in this case, we'll say web servers, have an IP address, and then your DNS servers will have a record entries for those IP addresses, but they'll all have the same fully qualified domain name. The DNS server can then cycle through these entries and distribute traffic. This is called round robin on Windows. Buying DNS has a similar process, but you can add a weight metric to one or more of the servers to impact how much traffic each one's going to receive. Content switches work at the application layer or layer 7 of the OSI model, and they're designed to perform certain functions. For example, they can handle web cookies, and that way they remove some of the workload from the web server. Quality of service, or QoS policies, allow you to prioritize traffic based on certain rules. For example, you can use it to control how much bandwidth a protocol or a system uses. Traffic shaping is a feature of quality of service where you can control the flow of packets into or out of the network according to the type of packet or other rules. If you want to guarantee or restrict a certain bandwidth or latency to a specific application, then this is extremely useful. Sometimes the throughput of a single port just isn't enough to transfer large amounts of data. Port bonding, also called link aggregation, NIC bonding, NIC teaming, port aggregation, and other names, is the idea of joining two or more ports together logically in a switch so that it's treated like a single connection, but the throughput is multiplied by the number of link connectors. Cisco has a protocol that you might hear about, and it's called Port Aggregation Protocol, or PAGP, which is common in an implementation of something called Link Aggregation Control Protocol, LACP, and it's defined by IEEE 802.1ax-2020. Let's talk about some of the additional protection measures that you might consider using on your networks. Intrusion detection and intrusion prevention are terms for the ability to detect an intruder on your network and then do something about it. Intrusion detection systems, or IDSs, are a system that inspects packets inside of your network and then it alerts if it detects something. An IDS runs in promiscuous mode, which means that it gets a copy of every packet on the network. That means there's going to be a slight delay from the intrusion being detected, but since the device doesn't sit in line with other devices, it won't impact the network traffic flow, even if it goes down. There's two types of intrusion detection systems that you need to know about. We have network-based IDS, or NIDS, which looks at network traffic patterns, and it tries to match that with a signature of a known attack. We have host-based IDSs, HIDS, which are installed on systems, and they monitor activity only on that system, like registry changes. And then we have intrusion prevention systems, or IPSs, which are very similar to intrusion detection systems, except for they're installed in line, which means that they can actually directly impact the flow of traffic or stop traffic if they go down. And second, an IPS can actually stop malicious activity. Just like with IDS, we have both host-based intrusion prevention systems, HIPS, and then we have network-based intrusion prevention systems, NIPS. Port mirroring is the ability to copy data from any or all the physical ports on a switch to a single physical port. These are very useful when it comes to monitoring traffic on dedicated systems. There's two types of port mirroring. We have local port mirroring, where you have to be directly connected into the port receiving copies of the data. And then we have remote port mirroring, where you can access the data copied without plugging directly into the switch. You could use a tap as an alternative to port mirroring, and this is a device that sits in line and it copies data to separate ports for monitoring. This way you don't have to dedicate switch ports to port mirroring, and these devices perform better under high loads of traffic. Proxy servers act as a middleman in between clients and external servers, and they process requests on behalf of clients. This is useful because the clients aren't exposed to external servers, and the proxy servers can filter out any unwanted traffic. Clients have to be configured to use a proxy server, which is usually in the connection settings or configuration of an application. Then when a client makes a request, the external web server actually thinks that it's the proxy server that's making the request and knows nothing about the client system. These are called forward proxy servers. Reverse proxy servers are another possibility, but instead the client requests information from the reverse proxy server and the server reaches out to other servers. The client doesn't know anything about the other servers, just about the proxy server. Proxy servers also can provide caching of content, which means that the first time a resource is retrieved from a website or location, the server can actually store that information, and if it hasn't changed, the next time that a client requests that same resource, the proxy server can provide the information a whole lot faster. AAA, or AAA, which stands for Authentication, Authorization, and Accounting, is supported by popular networking appliances to protect network access. This means that devices can support protocols like Radius, TACAX+, local authentication with a hard-coded username and password, or 802.1x port authentication. Many of these devices also support multiple failback or failover authentication methods. So for example, your primary authentication method could be a Radius server, and if that doesn't work, you have a local username and password for logging into the device.